Hello and welcome. Today we are going to discuss the chapter electric field and potential. So in this chapter we are going to discuss a lot of things like Coulomb's law and the forces between charges and the types of the charges, the unit of electronic charge and all that. So we are going to start with the electric charge. Now, when electricity was first discovered, people, some philosophers, they noticed that when you rub between certain kind of objects, they tend to repel each other. Sometimes they tend to attract each other. For example, if you rub a pen like this one uh, with your hair. Now I'm rubbing this, and you have some small piece of paper like this, and let us turn them into smaller pieces. So this will do. And if I bring them together, well, they need to be smaller. Now that I have paper pieces that are small enough, I'll rub this pen once again with my head. Now I'll bring them together. You see that this piece of paper jumped. This here, it jumped. Can you see? Well, it's not so evident under camera. This time I hope this will be clear enough. Yes, this thing jumps. You can see it. I can hold it with this pen. Look. So what is this force that we don't even know that this is a force up to this point. That what is this thing because of which these pieces of paper tend to attract this thing. Now the explanation that was given is that when I rub this pen with my head, with my hair, there are specific type of charge that is stored in here, and since they are electrically neutral, those pieces of paper, then there is a kind of force that just they are not actually neutral, but there are some kind of charges that are being induced here, and they tend to attract each other, and as they're when they attract each other, you have seen that when I take a bigger piece of paper like this one, the paper doesn't go up. The paper is not being lifted from this plane of the exercise book. That's because the electrostatic force that is being exerted, it's not greater than the gravitational force that is being exerted on this one. So this is very important to study the nature of the electrostatic forces, because you see everything around me, from my computer mouse to the light in my room, to everything that uses electricity. And although electrostatic forces are not so evident in our daily lives, but we'll soon know about the capacitors, which uses static electricity. So this is very important to know about it, and without having proper knowledge of static electricity, we just cannot study current electricity effectively, and there are concepts of certain kind of forces, we just cannot understand them without having a proper knowledge about this topic. So first I'm going to tell you the kinds of charges that we have. There are two kinds of charges. One is positive charge, and another type is negative charge. Now you you have to know this fact that there is nothing positive in this positive charge and nothing negative in the negative charge. This naming the positive and negative, this is completely arbitrary. It would make no difference if we started calling the negative charges the positive ones and the positive charges the negative ones. They are just two different categories, and this positive and negative, they are completely arbitrary. There is no need to think that positive charge somehow contains more charge than the negative one does. Now we are going to study some examples about which ones are the positive charges and which ones are the negative ones. So there are many subatomic particles inside an atom. Among those particles, for now we'll just know this name, the proton. This one is a positively charged particle. It has plus 1 electronic charge, and 1 electronic charge is 1.6 into 10 to the power minus 19 Coulomb. And if you want to know a better, a more accurate number, that would be 1.60218 into 10 to the power minus 19 Coulomb. Now coming to the example of a negative charge, we'll have electron has a same charge sign except for here this minus sign. So these are the two kinds of the charged particles. Now another thing I want to discuss is charge is conserved. Like the total amount of charge in the whole universe is constant. You cannot create some charge out of nowhere. Although this might seem contradictory to your recent experiences, like I just converted this electrically neutral pen into some kind of charged thing just by rubbing. Well, no charge was created in this process. All that has happened was transfer of charge. Electrons were in my hair, and from there those electrons were transferred into this, and that's how this becomes charged. There is no need to think that the electrons were created inside this. No electrons were created and no electron were destroyed. It's completely a transfer, and all the electrical phenomena you see around here, around you, those are all transfers of charge, not creation and destruction. Up next, we are going to discuss a theory of paramount importance in the theory of electricity, that's Coulomb's law. Now, Coulomb's law says about the charge, the forces that work between two point charges, and if we can simplify the cases for complicated bodies enough, it can be applied between any 2 points, any two charged particles that are away certain distances. So let us consider this charge as q1 and this charge as q2, and the distance between them r. So the force between them will be proportional to q1, will be proportional to q2, and will be inversely proportional to the square of this distance r. So this will look like this: F varies as q1, F varies as q2, F varies as 1 by r square. So if we combine them, they are going to look like this: F varies as q1 q2 by r square. Now you see, this is F is proportional to this mathematical expression, so we can just use a constant here and use the equal sign and write this as F equals k q1 q2 by r square. Now this k thing, it is replaced by a specific constant here, and that is written as 1 by 4 pi epsilon q1 q2 by r square here. Now this epsilon thing is called the permittivity of the medium, and since we will be taking most of our discussions in the vacuum, so we'll use the permittivity of the vacuum, and we'll write this as 1 by 4 pi epsilon 0. We'll write this. So epsilon 0 for vacuum has a specific value, and that is written as 8.854 into 10 to the power minus 12 Newton Coulomb inverse 2 meter square. And this 1 by 4 pi epsilon 0, it will be very good if you can memorize this term also, this value of this term also. So this will be 9 into 10 to the power 9. Sorry, I've written this unit wrong. Well, I'll correct in a moment. This will be Newton Coulomb inverse 2 meter square. Well, this will be Coulomb square Newton inverse meter inverse 2. And there is this short trick to memorize, to actually understand how this unit works. Look here, this will have the unit of charge, and this will also have the unit of charge, and this will have the unit of length. So this term here, it has the unit of charge square plus by length square. So that's Coulomb square per meter square. And we know that force is expressed in Newton, so this 1 by 4 pi epsilon 0, this constant will has to have the unit Newton per Coulomb square meter square. So this is a kind of a cheat code to remember this unit of both epsilon 0 and 1 by 4 pi epsilon 0. So I hope you understand the concepts up to this point, and up next we are going to discuss some more important topics. Stay tuned. Bye.